and the bass keeps running, running, and 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 in this context, there's no disrespect, so when I bust my rhyme, you break your necks.
Well, let's get it started in here with some graphing of linear inequalities, folks. Algebra 1 students, this is your 6.5 notes. We're going to get going here. I've got some different symbols over here. These are inequalities, and I'm going to act like there is a y right here for all of these. All right? The process to graph linear inequalities is very similar to graphing a line, but we are going to be shading on one section of the graph or the other. And so this is kind of a cipher, if you will, to know which direction of the line you shade it. And I also want to point out this can really only be done if your inequality is in slope-intercept form, meaning you have the y solved for. Okay, so in this case, in the first two, you've got y is less than, and in that particular case, you are going to have a dashed line. All right, which means that the actual line itself is not included in the answer. We'll talk about that later. We're going to shade below in that case. All right? Because y is all of these values that are below. All right? Okay. So we've got y is less than or equal to. That is going to be a solid line. And when we have y is less than or equal to, we are going to be in that same area. So we're going to be shading in all this. That's why our graph has that piece shaded in for us. So we're shading below the line. All right? And in the case where we have y is less than or equal to, it's a solid line. So I'm going to change our graph just a little bit. All right? Boom! Made our line solid. Okay. So in a case where we have y is greater than, we are going to have another dashed line. And we're going to be shading above in that case. So our graph would look something like this. We would have our line, we would shade in on the above region, and I need to fix that because I can't go down there below. Can't go down there below that line. All right, oh, and it needs to be dashed, so I totally messed that up. Let's get some dashed lines going in there. That a little eraser will fix that problem. There we go. So we have y is greater than or equal to. Now I can fill in that line and make it solid. Okay, now I've got a solid line, and I'm still shading above the line. So that's a little bit of a cipher for you when you're dealing with your linear inequalities. All right, so for number 1, it says graph the inequality. I'm going to pretend first that I've got this as a line, and it says y is equal to 1/2 x minus 3. And in that case, I would go 1, 2, 3 spots down and create my y-intercept there on my graph. And then I would draw a line, and my line would have a slope of 1/2. So every time I would rise 1, I would run 2, so I would have a line, or I'd have a point there and a point there. And if I was going to go the other direction, I'd have a point there and a point there. And since I have this inequality, let's switch to my laser pointer. Since I have this inequality where it says y is less than all of this, that means I'm going to have a dashed line. Okay, so my line is going to be dashed. Let's see if I can continue that. My line is not perfect because I'm drawing this by hand, but that's as good of a dashed line as you're going to get from Mr. Bear. So I have y being less than the line of this stuff over here. So that means that all of the region that is in below the line is possible solutions. The line is not included, but all of this region right here is possible solutions to my inequality. And I can get infinitesimally close to the line, but the line itself is off limits, kind of like when we did inequalities before, where the point itself was off limits. This time we're dealing with an entire line that is off limits. And some of you might be like, Mr. Bear, you really like to color because you keep coloring in on that graph, and you would be right. I do like to color. And there we go. All right, so in this one, I have an inequality that is in the standard form. So I could pretend like I've got the standard form of the equation of a line. So I've got negative 2x plus 5y equals 10. And if I was to use the cover-up method, I could figure out what my y-intercept is going to be. And I can figure out what my x-intercept is going to be. I can divide both sides by a negative 2 and say x is going to be equal to negative 5. That's going to be my x-intercept. If I use the cover-up method on the other side, I would say 5y is equal to 10. Divide both sides by 5. And y is going to be equal to 2. So I could plot those 2 points. 1, 2, 3, 4, 5. Negative 5 is my x-intercept, and my y-intercept would be positive 2. So I could use that point right there. And then I could make my line go between those 2 points. So let's see. 1, 2, 3, 4, 5, and 2. 1, 2, 3, 4, 5, and 2. I'm going to make another point right there. And this time, my line is solid. Okay? Now you might be like, okay, well, it's not in the slope-intercept form of the equation of the line, so I don't know which side of this line to shade. So what you could do is you could give yourself a test point and see if it makes that statement true. I'm going to pick a test point of 0, 0 whenever I can. It's just going to make my life easier. Okay? When I make x and y equal to 0, I have 2 times 0 and 5 times 0. So let's just go ahead and write this in. I would say 0 plus 5 times 0 greater than or equal to 10. Well, that's just going to be 0 is greater than or equal to 10. Well, that cannot happen. So I know that that test point is not in my possible outcomes. It's not in the solution set. So that means I'm going to shade everything northbound of that line. All of this stuff right here is your possible outcomes up there because my answer is not true when I tried out that test point. Now, if my test point was true, then at that point I would be shading everything south of the line. So that's one way to use a test point when we're dealing with the graph of an inequality. Okay, so this one is not a trick. I know some of you get spooked out or freaked out when you see something like this where it's like, hey, there's no y in that. How do I make that into a line? Well, x is less than or equal to negative 7. All right, so I'm going to go and find the point of x is equal to negative 7 and make my point 1, 2, 3, 4, 5, 6, 7. So that's probably have to recount maybe. Okay, so that's my point of x is equal to negative 7, or if I had, my x-intercept, x is negative 7. And I'm going to have a solid line, and so since everything on that line is a possible answer, that's why I make it solid. And the line of x equals negative 7 is what I'm going to consider, which is that entire line there. And x can be everything less than negative 7, so that means all of this stuff over here, all of this junk, everything over there, infinitesimally close to the line and including the line itself. Possible outcomes for number 3. All right, so for number 4 and number 5, the instructions are to determine whether the ordered pair is a solution of the linear inequality. So again, that's where we are going to plug in this point, this test point. I'm going to plug that into my inequality and see if it works, kind of like when we did a test point a couple problems ago. So this is my x value, this is my y value, okay? Let's get that out of the way so that you can see what I'm doing. All right, so I'm going to say 7 times negative 1 plus 2 times y, which is 1, is greater than negative 5. So this is going to be negative 7 plus 2 greater than negative 5. So we have 9 is greater than negative 5. Okay? So that works. This is a true statement. So we can say that it is a true statement, or we can say determine whether or not the ordered pair is a solution of the linear inequality. We can just simply say, yes, it is a solution. All right, so let's move on to number 5. We've got x minus y less than or equal to 3, so I'm going to go ahead and plug in my values. X, let's go ahead and put that in parentheses so you know that I plugged that in for x, minus y, so I'll put a minus 1 there, less than or equal to 3. Well, this is really the same as 2 plus 1 less than or equal to 3. And really, that's 3 less than or equal to 3. That works because we've got this or equal to part on the bottom, so that checks out as well. If this piece wasn't on the bottom, if it was just 3 less than 3, well, those are the same. They equal to each other. That would be a no situation. But we don't have that. We have this going on. All right? All right, so number 6 and number 7 say write an inequality that represents each graph. So pretty much every time I do these, I'm going to make my inequality in the slope-intercept form. I'm pretty much not going to try to do the standard form. It just would make more work for me. So I find the slope-intercept form to be pretty useful. Let's use it in this particular case. So this point right here, I can plot that point. That is the point of 0, 2. That is going to be my y-intercept, okay? Also my value for b. And I can count my slope using this point right here. My slope is going to be a negative 2 over 1. Okay, my rise is negative 1, 2 spots. My run is 1 spot. That's how I came up with my slope in that particular case. So if I was writing the equation of just the line, I would say y is equal to mx plus b, which is negative 2x, plus b, which is positive 2. But we're looking for an inequality, and because it's a solid line, I know that I'm going to be dealing with a y is less than or equal to, because the line is solid, and I also know it's going to be y is less than because this region here is shaded. Okay, so my y value has to be everything on this side of that. That tells me which direction my inequality is headed. All right, so then I just plug in the rest of my equation that I had figured out. Okay. And for number 7, I'm going to do the same thing, except for this line is a dotted line. So I'm going to figure out that I've got a y-intercept of 1, 2, 3. That's a y-intercept of negative 3. All right. And I've got a slope of, well, a rise of 1 and a run of 1, 2, 3, 4. So I've got a rise of 1 over 4, and that's a positive. So that's my slope. So I'm going to say that y is greater than, and the reason I'm going to say that y is greater than is because this region up here is shaded in. And I'm going to say greater than and not greater than or less than, or greater than or equal to, because we have a dotted line on there. So it's a dashed line. So the rest of my line, the equation of my line, looks like this. My m is my 1/4, so that's my slope. My y-intercept is negative 3, okay? So that is how we write an inequality that represents the graph.
Running and running, running. Come on, y'all. Let's get